Okay, here we go. We are on the west coast of Australia. And you can identify this boundary current just from the sea surface temperature distributions. On the left, you can see that there's warmer water moved. Warm is always in red in temperatures. Warmer water is moved along the coast, along the shelf break. This black line is the 200-meter contour, which is often good approximation of the shelf break. And you can see that the current moves along there. What you also can see are eddies that are created. You see these circular features. These are again mesoscale eddies. And if you don't believe it, it's always a good indication to estimate the scale. And if you end up with 100 kilometers, it is an eddy. Okay? Eddies are horizontal patterns, that are superimposed here on the mean flow, and you have horizontal movements around these eddies. Okay? And on the right hand side, it actually shows you temperature anomalies. So you derive an average field and then focus on the anomalies. And you can see some areas which have warmer water, shown in red. And you can see these eddies again. And you have areas which are colder waters. And you can see one here in the south as well. These are anomalies that are shown here. Okay, so what's the significance of these western boundary currents? I think I mentioned that before. Show it on the next slide. No, not yet. It's not the significance. Just before I do that, just look at the vertical structure of the Lewin current. The vertical structure. So we actually look at vertical transects here. Okay. Vertical transects cutting across the continental margin. So the coast is on the right, and there are three different properties shown here. One is temperature. In temperature, you can see the core of the Lewin current. It's the warmest water here. And you can see that it actually doesn't penetrate very deep. It's a fairly shallow feature, the Lewin current. Only extends to a depth of something like 150 meters, 200 meters. You can also see that it moves lower salinity along the shelf break. You can see that here in the salinity on the right. And on the left side actually shows you this is the density in terms of sigma t. Okay. I should also mention that the Lewin current itself is poor in dissolved nutrients. Okay, it's a very nutrient poor current, and it only induces a upwelling in interaction with bathymetric features like the Perth Canyon is known to be fairly productive because of the interaction of the Lewin current with the feature. But I actually wanted to tell you about what's the significance of these western boundary currents, and this is they can create marine heat waves if they are stronger than usual. Okay, and this is one example of a time when the Lewin current created a significant marine heat wave in surface waters. And this is in 2011. That's when it happened. Okay, just going back to the right slide. Sorry about that. And this is shown here. Okay, so this marine, and indeed such heat waves, and here's a time series. Okay, this is a time series, and if it prolongs for a heat wave like this, prolonging for several months, indeed can have a significant implications, and significant implications for the marine food chain in that area. So heat waves. Okay. What drives the Lewin current? It's not directly the wind. It's not the coastal wind, because the coastal wind actually suppresses upwelling. The wind along the coast of Western, the average wind, what actually creates this feature of the Lewin current are the winds and to the north of Australia. Okay, so on the northwest shelf in the Arafura Sea, that actually create indirectly the Lewin current, which is a year-round feature. Okay.